All right, so let's get started with this short lesson today. And this one is on, we'll first start off talking about normalizing deviance and self-deception in engineering. So designs can kind of carry standard predictions about performance, but sometimes these performance standards of a product are not met. So when these predictions are not fulfilled, engineers sometimes don't correct the design to account for the prediction about performance not being fulfilled. They don't correct the design, but sometimes they just accept the anomaly. So here an anomaly is an aberration. It's something that's out of the norm. It's something that doesn't fulfill the common prediction or the standard for performance. They might just kind of accept the anomaly without thinking twice about it, without trying to correct the design, or they might increase the boundaries of acceptable risk. They might say, oh, well, this is an aberration, this is an anomaly, but let's just expand our boundaries of acceptable risk and let's just say it's okay and let's just keep going on with our day-to-day business. So these are problematic actions, right? When the predictions aren't being fulfilled, especially when the product can lead to safety risks and the like. In these kinds of situations, engineers should not just merely just accept the anomaly, accept the aberration, and just go on their way, or increase the boundaries of acceptable risk to be able to account for the anomaly and then just go on their business. To give you an example of this, let's return back to the Challenger disaster. And remember, there were problems with the O-rings that were in significant part responsible for the Challenger disaster. So NASA didn't predict that the O-rings in the Challenger disaster, the O-rings that were used on the Challenger, would be touched by the hot gases of motor ignition. They didn't make that prediction. However, previous flights showed relevant damage to the O-rings from the hot gases of motor ignition. So this is an anomaly. This wasn't part of this kind of standard prediction. However, NASA just accepted the anomaly without trying to fix it. They just kind of accepted it and didn't think twice about it and just went on their business. They should have done something about it in this case. Also, the lowest acceptable temperature for the O-rings was 53 degrees Fahrenheit. And remember, the morning of the actual launch, the temperature was 29 degrees Fahrenheit, over 20 degrees difference in what was lower than what was acceptable as far as temperatures for the O-rings. However, what ended up being the case overall, the NASA as well as the O-ring company, they accepted or they expanded the acceptable boundaries of risk dramatically, right, by over 20 degrees. And that day they said, oh, well, 29 degrees Fahrenheit, okay, let's say that's acceptable risk, and let's keep going on our way. So here we can see how these kinds of actions, when we see these kinds of aberrations and anomalies in what's expected, that these kinds of actions are problematic. And engineers should put in the extra work, right, to try to fix the problem and look deeper into it. And sometimes engineers can be caught in a kind of catch-22 where you're kind of damned if you do, damned if you don't. So engineers sometimes may put themselves at legal risk even if they try to provide extra safety, such as extra safety to their workers. For example, trenches may be used when excavating for foundations, pipelines, and sewers. So what we see, the picture on this slide is we see a trench, right, dug into the ground. And trenches are unstable, where the side walls may collapse. And if there are workers inside the trench, then that's going to lead to problems, right? And workers can die. However, if you add in a trench box, which is the thing in red that you see inside the trench, that can add a significant amount of safety for the workers. So it looks like this is a good idea. It looks like this is a good idea. However, if trench boxes are not required by building codes and by the laws, then the engineer can be liable for any injuries that may come from the use of trench boxes. If there's a kind of freak accident where the trench box is in significant part one of the reasons why a worker got injured, then the engineer, the kind of head engineer in this case, can be liable for that because the box itself wasn't required by building codes. So it seems like here in this situation, if the engineer puts in the extra work or the extra kind of effort as far as creating safety in the workplace, this potentially could lead to problems for the engineer, legal problems for the engineer, if it's the case that these trench boxes are in significant part responsible for an injury. And also, if no boxes are used, if the engineer says, oh, you know what, because of that possibility, I'm just not going to use any trench boxes, then the engineer puts the workers at greater risk as far as the trench collapsing on workers. So it's, we have this situation here where if you use it, you could get into trouble. If you don't use it, then it could lead to loss of life or serious injury. So at this point, I'd like for you to press pause and think about what might be done in this kind of situation. What might be some kind of moves that the engineer can make in this particular case to try to get around this kind of problem. Okay, and so there could be various possible solutions to this problem. And one of them is that the engineer can, as well as the overall larger business or corporation, can lobby Congress to pass laws saying that trench boxes should be used, right? And in that way, if there is some kind of freak accident where it's the trench box that causes damage, physical harm to a worker, then the engineer is not liable because it's required of the engineer to provide trench boxes for the workers. So that's one possible way to get around it. All right, and so as I said before, this is a short lesson, and so that's all there is for this particular module, and I will see you for the next one.